Hi, everybody. Well, let's pick up our story again. So now we figured out how we can write Schrodinger's equation in spherical polar coordinates. Here, let's take a look at that. Okay, here we are. So the formula looks very complicated, but we can recognize what's going on. This very long term here is just del squared psi. So we have minus h bar squared over 2m del squared psi is equal to E minus U times psi. It's just the equation that we've used before. It only looks complicated because we've written it in spherical polar coordinates, the del operator. Now, we're going to do the same trick here that we used when we solved the particle in a box problem. We're going to look for separable solutions. If we have a potential that's spherically symmetric, there should be separable solutions that have this form. And those are going to turn out to be the energy states, the stationary states. Okay? And so in order to do this, we substitute this separable solution back into Schrodinger's equation and turn the crank. And just to be clear, what we're saying is that psi of r is equal to one function that only depends on the distance from the origin. We'll call it capital R of r, times another function that only depends on the polar angle. We'll call it capital theta of theta, and a third function that depends only on the azimuthal angle, capital phi of phi. We substitute this into Schrodinger's equation and then turn the crank, and this complicated looking partial differential equation is going to split up into three ordinary differential equations, which will be easier to solve. The first is the phi of phi equation, and we find that the second derivative of capital phi with respect to phi is equal to minus m squared times capital phi. And we know enough by now to recognize that an exponential function will solve this equation. Okay? So the solutions look like e to the plus or minus I times m times phi. But there's a boundary condition. If we go all the way around the azimuthal coordinate from 0 to 2 pi, the solution, the function has to go back to its original value because it has to be continuous at the origin. Well, it has to be continuous at everywhere. So that means that the value of the function at a angle phi has to be equal to the angle to the value of the function at 2 pi plus phi. And the only way that can be is if m is an integer. So in this case, m can take on values 0, 1, 2, 3, 4, and then we have solutions that look like e to the plus or minus m times phi. Okay? So m is quantized. It's our first quantum number for the central force problem system. The second equation looks more complicated here. It's this one, the second derivative of the theta function with respect to theta plus cotangent of the theta function with respect to theta is equal to minus m squared cosecant of phi of theta times the theta function. Minus m squared times cosecant theta times the theta function. All of this is equal to minus L times L plus 1 times theta. Okay? This looks kind of complicated to us, but in fact, the form of this differential equation is familiar to applied mathematicians, and so the solutions are well known. The solutions are a set of functions called the associated Legendre polynomials, right? Of course, just what you were thinking, right? But again, this is a familiar set of functions. They're tabulated in Mathematica. Let's just take a look at them. They look a little, okay, so theta of theta is equal to a constant times PML of cosine theta. So it's associated Legendre polynomial, and then the argument is going to be cosine theta. Here are some of these polynomials. P00 is just 1. It's a constant. P01 of x is just x. It's a linear function, but it's the simple one. But there's another linear associated Legendre polynomial, P11 of x, and that has the form minus square root of 1 minus x squared. Also a linear function, okay, but a little bit different. And so on. Here's P02 of x, 1/2 times quantity 3x squared minus 1. And then there's this one, P12 of x, minus 3x times quantity 1 minus x squared to the 1/2. And this one, P22 of x, which is 3 times 1 minus x squared. This is probably not telling you a lot to look at these polynomials, but I just wanted to point them out. Notice that there are now 2 quantum numbers, m, which we've discussed, and L. L is a second quantum number, okay? And the Legendre polynomial depends, its form depends on the value of both m and L. Okay, now I'm going to show you some plots of these functions. And what I'm going to show you is actually the product of these two. The product of the theta function and the phi function, because these are really well known. They come up in many different types of problems. The product of these two has a name, and they're called the spherical harmonics, okay? And so I thought I'd show you a table of the first few spherical harmonics and a plot of this. So this table is from our book, okay? The lowest spherical harmonic, y00, L equals 0, m equals 0, it's just a constant, okay? Y01 is a constant times cosine theta. Y plus or minus 1 is a constant times sine theta times this factor, e to the plus or minus I phi, and so on. But now let's look at some plots of these. So for the y00, a plot of this looks like this. Its amplitude is independent of angle, okay? So it can be represented by a sphere, all right? The next one is proportional to cosine theta. So it can be represented by this. So the amplitude depends on the polar angle only. It's a maximum when that polar angle is 0. And then as the polar angle increases, it gets smaller and smaller. When it's 90 degrees, the cosine theta is 0. And then when cosine theta is larger than 90 degrees, it becomes finite again. I'll just mention what's plotted here is actually the square of the function. So it's always positive. That's why it has this form, okay? But it looks like this. Here, let's look at the next one. Y1 plus or minus 1, 1. So y, L equals 1, m equals plus or minus 1. It looks like this. So it varies like sine theta, okay? It starts at 0, and then as the polar angle increases, it gets larger, it reaches a value of 1 at 90 degrees, and then it goes back to 0. And then the amplitude should depend on this azimuthal angle because of this term. But again, we're looking at the absolute value squared. So this term drops out, okay? So it looks like a figure of revolution in the azimuthal angle, or like a donut, of course, okay? Let's look at the next few. Here's the y02, m equals 1, L equals 2, m equals 1, m equals 2, L equals 2. Here are these. Again, we're plotting the square of the function. Now, the reason I plotted these is because I bet these shapes look familiar to many of you, okay? Most of us have had some chemistry class in this before, and so you know what the shape of, well, what do these look like? These look like the shapes of atomic orbitals, okay? So it's interesting, but the spherical harmonics, plots of the spherical harmonics look like atomic orbitals, okay? And that's not an accident. All right. Anyway, this can help us to picture what these functions look like. But what these are showing us is how the solutions, in this case, the solutions to Schrodinger's equation, the different types of solutions you can have in a central force problem, how the amplitude varies with polar angle and azimuthal angle. And for central force problems, it looks like atomic orbitals, okay? The third equation is the radial equation, which I've just plotted here. And have a look at this. This looks a little more complicated, but I'll just read it off. It's minus h bar squared over 2m times this term, second derivative of the r function with respect to r squared, plus 2 over r times the first derivative of the r function with respect to r. Plus, there's a second term that contains the quantum number L, h bar squared L plus 1 times quantity L plus 1, excuse me, divided by 2m r squared times the r function. And all of this is equal to E minus U of r, potential energy, times quantity times the r function. Something to note, because the potential energy only depends on r, the angular wave functions, angular part of the wave functions are the same for all central force problems. However, because the potential energy appears here and the potential energy function is different for each different problem, the radial part of the wave function is different for every different central force problem, okay? By the way, now can you see why those solutions looked like this? Why the angular part of the wave function looks like the atomic orbitals? It's because it is. The, the hydrogen atom is a central force problem, so the angular part of the wave function for the hydrogen atom has to look like this, okay? But that's also true for all the other central force type problems that are out there. Okay, very good. Let's stop here for a moment.